This is the sub-lecture of the first part of Chapter 7, so it's on design tools, and this little bit talks about river routing. And basically it's in cases where wires are not crossing, and so it's a simple river routing algorithm could be quite effective. And the basic idea behind this is it sort of keeps the buses together, one of the things that one would like. So a simple example of it will be shown here, or shown next, but the basic idea is if you're inserting a jog, that jog kind of propagates to the other wires which are nearby. And doing this, you hopefully can obtain a well-structured route for a bus, and hopefully most of the wires would be of minimum length. So it's not really applicable to scenarios where wires have to cross one another. This is just a simple little example taken out of electric handbook from years ago, and it sort of shows where perhaps you had to include a jog here for a design rule violation reason, perhaps, then the jog could tend to propagate. So that's sort of the idea behind it. Now we want to talk a little bit about FPGA routing considerations. In the case of some FPGAs, one would like a good mix of routing resources, some long, some short, some medium, and you can sort of justify the reasoning for that is that you're going to probably need a mix of routing resources when you go to route up any arbitrary kind of design. And the idea behind the FPGA is the ability to route something that is arbitrary design. If you have too many long lines, then that would be quite wasteful. And too many short lines would be wasteful as well, because you'd have too many switches to connect up long lines. So as a consequence, you need to have some mix. And this is typically arrived at empirically. So you place and route a whole bunch of benchmark circuits and try to optimize the architecture. So here's a simple example of FPGA routing. Obviously you can see that you'd have lots more of load capacitance to account for and try to minimize, due to the extra wiring, which is illustrated in red here, and diffusion, which is not exactly shown here, but you can guess that at every time you've made a transition like this, you've had to go through a switch, and that means you have source and drain regions which are both diffusion, so a fair bit more capacitance associated with them. So this might be the route that you want, that's shown in black here. And but since you're routing it in a reprogrammable architecture, you have to account for all of these extra bits of capacitance that perhaps you wouldn't have if you were building it in an ASIC and not an FPGA kind of environment. So these were wires here which were, let's say, horizontal and vertical. So all of that additional capacitance had to be accounted for. If you look at a little tiny place like this where you might have a switch, well, basically the switch is programmable, so a D-type flip-flop perhaps is controlling whether this switch is on or off. But in any event, this is a signal channel you want it. You can see this is that extra parasitic capacitance that you didn't want, and you have to also account for the parasitic capacitance of the source and drain region of that transistor, as well as any other switches which are along that route that are not turned on. You still have to account for the diffusion of the place that is contacting the metal. So you get a lot of extra R and you get a lot of extra capacitance with an FPGA. Other things that you might want to consider, and these are kind of future, in quotes, routing algorithms. These are kind of biology inspired. This is called ant colony optimization, relatively recent, in 2007 kind of thing. And what they were trying to do was try to come up with something that's going to try to minimize this active power. So they get some kind of relatively simple equation where they have an activity factor times C v squared f, which we've already figured out why that would be the case. And the activity factor basically would be related to how often that particular module is toggling on and off. So you basically determine A empirically. And then they come up with a calculation for the capacitance of a routing wire as being approximately 0.2 femtofarads per micron. Average capacitance of via was 0.23 picofarads, so the capacitance we minimize using some type of a cost function. So in this case, the cost function is just related to the length of the wire that you're going to have to connect up and the number of vias. So for ant colony optimization, as you might imagine, it's sort of this multi-agent framework where basically a number of ants would be seeking to find the shortest path. And in nature, ants achieve that through even though it's local communication, it's basically through a substance which is known as a pheromone. And as a consequence, you might be able to employ something like this, which they did in that paper above, to try to come up with a nearly optimal routing kind of configuration. So the kind of things that you'd have to worry about, of course, are vias and the cost associated with the vias and the lengths of the wires. You may be able to think of other routing algorithms that are nature inspired. Certainly, I'm sure this probably is not the best one by any means, but it just gives you an opportunity to think about something a little bit outside the box. And it's an analog, and engineers typically are pretty good at figuring out analogs and figuring out how to exploit them. Some other things related to the ANT thing was, ANTs only have local communication, yet the results are global results in terms of their nets, no centralized control. Maybe those are good things to implement an algorithm. They multitask in reality, various details assigned and assumed. And just one other little thing to point out at the bottom, that maybe this is going to work because all the ants tend to be female. There's very few male ants out there to clog up the works. And anyway, in summary for this section, we looked at some design tools which attempt to exploit certain fundamentals. Often these are common sense. They're certainly not new by any means, but they're still very important. Divide and conquer, reuse, hierarchical design, and the ilities, such as making something more reliable or maintainable. Tools exist at all levels. We were primarily looking at low-level kind of things here, but there's certainly tools for optimization at every level that you can think of for an integrated circuit. I would say that you should be familiar with simulated annealing with respect to an engineering algorithm. It's an intelligent option in almost any scenario of combinatorial optimization, with the exception of something like DRC. And this is the end of that section.